Hello world, this is Craig. My Prompt 48 is on the fritz. Now the Prompt 48 is a programmer and development machine that's for Intel's 8048 family of microcontrollers. They also made the Prompt 80 for the 8085 family. Now I didn't get very far working on this before I got distracted with the memory chips. This board has 4 memory chips here and 2 memory chips up there. And it's extremely unique in that these memory chips, they're made by Intel, and they're only found in 2 products in the world. So Intel made this memory chip, shipped it in these 2 products. It was only used in-house. One product it was used in was this Prompt 48, and the other product it was used in is this single board computer. This is the 8020. So this is the single board computer that came out right after the 8010. So they made the 8010, the 8010A, then they made the 8020. So this 8020 single board computer and the Prompt 48 both use that memory chip, and they're the only 2 products that do. And you won't find that particular RAM chip in any of the Intel data books. If we go back to 1975, EM&M was the first to introduce the 4K static RAM, and that was so early in 75. EM&M was Electronic Memories and Magnetics. Later they became part of the Titan Corporation that was then merged into L3 and I think is now part of Harris. So 1975, and then in 1976, AMD started shipping 4K devices, and within a year, MasTec, NEC, Signetics, and TI were all shipping 4K static RAMs. Intel, meanwhile, was working on their static RAM, their 4K static RAM, and it's the 2114. But Intel was having a horrible, terrible year in 1976 for these RAMs for some reason, at least with regard to this one particular 4K. Now this was a 4-bit wide 1K static RAM, and it wouldn't be until the second quarter of 1977 that Intel finally got the 2114 process tuned and began ramping up full production of these RAMs. Meanwhile, everybody else, it seems, was already had a 4K out on the market. So if we look at the die, we can see there's a lot that can go wrong on this chip. I don't know how many transistors this has. It'd be nice to know what the number of transistors this is. Before we go on with the story, let's orient ourselves with this die. So pins 1 and 18 are at the bottom of this image. So this is pin 1 down here, and then we go counterclockwise around the chip. Pins 2, 3, and 4 are all row address lines. So we can look at the data sheet for this. We have the row address lines, the column address lines, chip enable, and a write enable. Generally, all of the row select business is going on at this bottom end of the chip. Then here, if we look at the other end, we take over, we were on pin 4, so this is pin 5, 6, and 7, which are now column select address lines. Then this is the chip select, and this is the ground, which is pin 9. This next pad bonds to the substrate, and I'm not sure if this is a back bias generator or what's going on here. I presume it's an oscillator to generate the negative VBB for the back bias. Because after all, in this family, the minus 5 volts wasn't needed anymore, and they did that by generating a back bias on board or on chip. Then we have the write enable, and these last 4 here on the top are the data I/O lines. So these are bidirectional. It's a 4-bit wide memory. The column select and the data I/O are all kind of confined to this end, and I would consider the chip select and the write select to be included in the data functions. Now back to the other end, if we follow the chips around, this is address 9, which is the 4th column select, and you can see that it runs all the way to the other end of the chip along the side here to do its business down on the column select end. Now if we back out and look at the whole chip again, a few features become noticeable. The bottom is the row select. The top is the column select and the data I/O, and all of this in the middle are the storage cells. And there's some noticeable horizontal connections, and each of these connections services 2 storage cell rows. If we count up, there's 32 of these horizontal features, and since there's a data cell above and below, that gives us the 64 rows of this array. And these rows go all the way across. The next thing to notice is there's a trunk line of signals coming up the center. And if we go back and we look at the chip data sheet, each row select is a differential signal, and we can see that if we look closer at this vertical trunk, the cross connections and transistors here are going to select a specific row when these 6 row address lines match the hardwired pattern that's seen here in the trunk. So we're not looking at transistors, we're just looking at these vias and presuming that, okay, if there's a via, then it's doing something. And so each of these intersections are basically comparators. When the applied address matches the hardwired address, that row is selected. The next thing to notice is that the chip is divided into 4 quads, and they're divided by these larger vertical power rails. If we go back up to the top of the storage array, we can see these horizontal trunk lines, just like the vertical ones. Now these horizontal ones are the differential column address signals. There are 2 lines for each column address, so a total of 8 signals are coming across this trunk. And they're not evenly distributed because there's some larger power rails in the larger gaps. But if we count them up, there's 16 select lines in each of these quads. Now note that the address select pattern, according to the vias again, are the same for each quad. So these quads appear to be accessed in parallel. Now I haven't completely traced them to the output since I can't see properly, but I would suggest that each of these quads is the storage for 1 bit. So a row is addressed, a column is addressed. The data from the 4 selected cells, 1 in each quad, will come up through this mess of transceivers here above the column select trunk. And if the chip is selected, or if the chip select is asserted, then that data will be fed into these huge output transistors here to output on the 4 data lines. If it's a write cycle and the chip select is asserted, then the data applied to these 4 data lines will make its way through the transceivers and to the addressed data cell where it's latched at the end of the write cycle, which is either the write chip or the chip select is deasserted. Now to back up a bit, I presume that the way that the address and the column row selection is going on here is that the 2 differential lines are actually the address and its inverse. Then the FET makes a selection of one of those 2 where the via is put in. And so for each of these, the addresses, either the address or the not address, they're logically NORed with all of the other row select addresses. Well, actually, since this doesn't end with an A suffix, one expects that this to be enhancement mode, so I guess they were logically ANDing the addresses, I suppose. So check me on that. So these addresses come up. For each of these rows, they've selected a combination of either the address or the inverse of that address, and when those are all true, then it selects, they're ANDed together and it selects that row. And if you really want to get into the details of these, look at the 1973 and the 1977 memory design handbooks. They go into fairly deep details as to what each cell looks like and sometimes how they're selected, although they don't have the 2114 in that. The 1977 one has a section specifically on static RAMs, including the storage cell configuration. So I also want to acknowledge Ken Schrift's fantastic blog in Reverse Engineering Devices. And I also sent the die photos to Ken, and he graciously answered some of the questions I had. And since we can't see through the top metallization layer, Ken suggested that I remove the passivation glass in that layer to see the transistors better. And until then, there's a lot of open questions about this. But maybe if we all ask Ken, he'll do a full reverse engineering on Intel's 2114. I suppose in the grand scheme of things, 2114 isn't a particular historic chip, compared to something like the 1103, for example. But maybe we could generate his interest. Okay, so back to the story. So we were in 1976. Intel was trying their best to get these 2114 4K RAMs into production. Now, Intel was also in 1976. They were starting up their brand new fab facility, which is going to be the first in Oregon, down by Portland. But while that may have been a distraction, that fab line was not the cause of these poor 2114 yields because Intel wouldn't even move their memory components group to Portland until the late 78, maybe mid 1978. As another distraction, a side story, if we were to jump ahead a couple of years, there was a little bit of 2114 industrial espionage going on. And there was an indictment handed down that I came across when I was looking for information on the 2114, where some bad actors had stolen fabrication materials for the 2114 from Intel and also from National Semiconductor. They were then selling things like reticles and mask overlays and mask design pattern generator tapes for the 2114 to undercover agents. But I think that was the 2114E, so by then all of the Intel's production problems were over. So if it was 1976 and you were in the Special Products Division of Intel's Memory Components Group, it was a pretty grim situation. It seemed to be specific to dialing in the 2114 process, which is just plagued with poor yields, and Intel simply could not get the 2114 launched. In fact, in 1976, Intel was buying 4K devices from other manufacturers to support their board-level products. Intel shipped an estimated 2 million 4K ROMs in the first quarter of this year, so this is 1977, the year after the problem, and slightly higher number in the second quarter. Intel's problems with production of 4K RAMs in 1976 have been long resolved. The company now offers a full line of devices, both 16 and 22 pin, with the range of differing speeds. It's no longer buying fast 4K devices to supply the needs of its memory systems division. And that really had to have hurt to have that come out in the 1977 analyst report. So in the 75-76 time frame, Intel put out the 8010 single board computer, but it had been designed before the 2114 was anticipated, and so it does not use the 2114. It uses the 2111, which is a 256 by 4K. Okay, then shortly after that came the 8010A, and it uses the 2102s. So again, they avoided the 2114. So now they wanted to come out with the 8020, and it was going to be designed around the 2114, and so was the Prompt 48. So you can imagine that the board and systems level groups, they're trying to design products around this 4K, but all through 1976, the memory group is cranking out 2114s with unacceptably low yields. Now, when a process is having random failures that don't impact the operation of the entire device, you'll obviously increase the failure or increase the yield if you can ignore that particular failure. And as a clear example, if you look at the early 2708 EEPROMs, if you go through a complete fab process for a 2708, but you have a bad bit in the top half, you can take the fallback position, which is to sell it as a 2704. There's a logical market for the 2704 between the 1702 and the 2708, and at a reasonable price point, there's a sustainable market. So go ahead and take the chip, take the defects that are half dead, and sell them as a new chip. If you can't fix it, then go ahead and feature. I have some 2704s I got out. Yeah, these are 2704s, and if you actually look at these dies in the microscope, they're marked as 2708. They're bonded exactly like a 2708, and in fact, yesterday, just as a test, I went through and I programmed all of these as 2708s, and they all program. So even though these are labeled as 2704s, they're fully functional 2708s. So these were obviously made after all of the problems making the 2704s had evaporated, and they were only making 2708s. They were just, or marking them as the market dictated. Okay, so back to the 2114. Getting all of the bits to work in this thing, at least with any respectable yield, just wasn't happening. Now, you can imagine if you're at Intel and corporate starts writing down profits for the year, and one of the largest memory manufacturers in the world is buying memory chips from competitors because their own 4K devices just aren't working. And there's piles of chip carriers with half-working, half-dead 2114s that are cluttering up storage. Something needs to be done. And if you're working in this group in 1976, tell me if I'm overstating just how grim the situation must have been. And I wouldn't have even wanted to be a fly on the wall when the decision was made to just take whatever half-working, half-dead 2114s there were and start shipping them over to boards and systems so that they can finish up their product design and start shipping products, specifically this Prompt 48 and the 8020. In fact, if you look at the early schematics for this board, it appears that they are planning on using a pair of 2114s because they have A0 come in and it's decoded into two chips. So the two 2114s, that would give them 4K of memory. But what they had to do was they have a little piggyback board that then takes A0, expands it out with a little decoder so that they can use 4 2113s instead of the two 2114s. And then this little piggyback board just has a jumper for A0 either low or high. Now on my board, it must have been made a little bit later. It was made in 77, I think, but if you look at the schematics for it, this board actually shows the 4 chips for the 2113, so it doesn't use the piggyback board. So if you have a prompt, it'd be interesting to know if you have that piggyback board or if you have the 2113s on the board itself. Now for both of these, they have it marked in the schematic for this other memory as a 2113, but I would guess that those originally were 2114s, and they just said, well, for that particular memory, we can live with half a K in this if we just directly go from the 2114 down to the 2113 without having a piggyback board. And then all they had to do on the older schematics was to take the A0 line and run it to a jumper rather than A0. When you find a 2113, it'll either be marked as A0 low, which is what this one is, or these are all A0 high. These 4 and these 2 are all A0 high. So that means that in order to get this chip to work properly, you have to tie A0 either low or high. And the bad half would be in the other half, the part that you're not using. So when these 2113s are designed into a system, that address needs to be tied either up or down depending on which flavor of the 2113 was being installed in that board. So in both of these products, there's a jumper that allows you to select if A0 is going to be low or high. Now if we look at the die again, I think I was able to trace address 0 to this bottom pair of the column select lines. And this is where the choice of A0 makes sense. Let's look at the column select pattern. The top 2 have a different select configuration for each column. So that, in essence, is the least significant bit of the column address. Now, once you're inside this array, it doesn't matter if, which addresses connect to which, because any particular bit enables or disables half of this entire array. Whatever bit this is, it changes the most frequently across this quad. Then they progressively change less and less frequently until we get to the bottom pair, which only change once. So what I'm referring to are these vias. Remember, each column will utilize either the address or its complement. So looking at the top 2 traces, you can see that either the top trace or the second trace has a via, and that changes for each one of the columns. So top, bottom, top, bottom, top, bottom. If we jump down to the bottom 2, we can see there are 8 columns that have the same configuration. The bottom trace is untapped, and the top trace has a via for each column, meaning it's being used to select that address. Those traces here to the left are reversed. The bottom has all the vias. So if this indeed is A0, it means this left 8 are, let's just say, A0, and the 8 to the right are then not A0. Now, why does that make sense to me? Let's presume that the process defect is localized to a specific region. This bottom address line is the one that creates the largest physical region on the chip. And therefore, it gives the greatest probability that if this is a regional defect, that all of that regional defect problems are within that bit's control. So with A0 being the control bit for the 2113, it means that any defect that's in the entire left or the entire right of this quadrant is mapped in or out by A0. So if you have a defect over here that's affecting 10 cells, but they're all on the left half, those would only be affected by A0 equals 1. And if that whole region is only on the right half of that, then it would only be affected by A0 equals 0. Now, of course, if that region right in the middle, then this whole chip has to get thrown in the garbage. So in this entire chip, this bottom address line creates the largest physical area that's controlled by a single bit. And that's why it's chosen, I think, as the bit to control which half of the 2113 is used. Any other bit would have further reduced the overall yield of the already half-dead 2113s. So now while the 2113 was a stopgap to Intel to ship their 8020s and their prompt 48s, for all practical purposes, 2113 was considered dead to Intel, and they would never acknowledge this chip, and its name would never be spoken again. If you look at the catalog pages for any systems or board level products, Intel typically, if not always, mentions which memory chips are being used in that product. But for the data sheets on the prompt 48 and the 8020, they're completely silent about what RAM is used in this. Of course, it's in the schematics, but it never shows up in print that the 2113 is used in these two boards. If we go back to that little bit from the industry analyst, it says by the spring of 1977, the 4K crisis seemed to be over. I pulled these chips out and I tested them. So I pulled out these 4, these 2, and this one AOL that I have. So the ones in here are AOH, and they should be fine with any odd address. So anytime that the least significant address bit is high, you should be able to read these just fine. So I took those and I put them in my 8010B. As I mentioned in earlier videos, my 8010B is my favorite Intel workhorse, and these are the RAM chips in it. And so I took one out and I one by one I swapped them with the chips in this board, and then I did a memory test. And I thought that was interesting enough to share, and I wrote down the results of that over here. Okay, so this one on the far right had 2 bad bits, and they were both stuck at 0, and they were in addresses 92 and 192. And I thought it was interesting that both of those bad bits were only separated by A8. Now this one to the left had every even address stuck at logic 1. So the entire A equals 0 side of this chip is dead. So here where we only had 2 bad bits, this entire half is dead. The next one had a single bit that was stuck at logic 1, but it was intermittent. Sometimes it worked and sometimes it didn't work. And then this one on the left had a 1 stuck bit again, and it was stuck high. But an interesting thing about that is it didn't show up until I had done, I think, like 4 tests on this, and then it was consistently stuck. So for this one, there's some sort of, tunneling or leakage or some kind of charging that caused this one to work well initially, but then if it was cycled enough times, then it charged up, and then after that period of time, it always latched itself high. So this one had a high latch up problem. As I mentioned, this one isn't from this prompt. It's a AOL version. And when I tested it, there's a single bit in the bad side that was stuck at 0. So this one only had a single bit error, and so it's actually the best of all of these. Now this AOL was week 13 of 77, and all of these 6 in the prompt 48 are from the first quarter of 1977, except for this one at the top, which was from week 35 of 77. Now the funny thing about these two, all of these had the problems I mentioned. The funny thing about these two, one of them was from the first quarter, I think it was maybe week 9, week 7. And the other one was from week 35. Both of these were completely good. I tested these several times and neither one of them indicated that they have any problems at all. So if Intel had solved their problem by the first quarter of 77, then this one from week 35 would have been just marked as a 2113 just because that's what the BOM called for. They had, from their products group, they had orders for the 2113, so they marked this as a 2113 even though it's a fully functional 2114. This one over here, made in week 7, it must have just been made when the stars and planets were aligned because it is fully functional even though it was only made at week 7, which actually was before all 4 of these chips. Now for future knowledge, let's look at this 8020 again. So when Intel got the fully functional 2114, they came out with the 8020-4. So this is the 8020-4, but it is not to be confused with the 8024. Okay, so this is the 8020. This is the 8024, and this is the 8024. As another interesting side note, now I have no idea how this actually fits into the story, but Harris Semiconductor followed Intel and also released a 2113 equivalent. It's the Harris 6513. It's 2K 512 by 4-bit chip, and it also comes in the 6513H and the 6513L versions. And when they have it in their 1978 catalog, they just cross it over the 2113. So even while Intel considered the 2113 to be dead to them, Harris was offering an equivalent. And who knows, maybe it was just to rub Intel's nose in the whole business, but the fact that Harris offered a 2113 equivalent seems positively insane since the 4K crisis only lasted a year, and if you don't have a 2113, you just put in a 2114 since the board doesn't know the difference. So maybe someone who was out there with Harris at the time can help that make sense. Why would Harris make a 2113 well into the early 80s? I think it shows up in their 1981 catalog also. Okay, well that's it for this video. I'm back to working on this prompt 48 so I can get it going. I've got a prompt 8048 project that I want to work on. So if you have any 2113s or if you have any insight to the 2113s, let us know what you think about it. Alrighty, thanks for watching. I will talk with you later. Bye-bye.